Sound, a curious and astonishing phenomena we take for granted, providing communication, music, and the very loved sense of hearing. We are always listening to the world, yet we may not realize that what we are actually doing is taking a very low signal and amplifying it for ourselves. This idea has now been utilized in electronics today. For example, how do we turn this into this? It all boils down to the transistor. This was a new invention that is now used in our phones and computers to calculate complex calculations for everything.
Now, in today's world, we use something called an audio receiver, which very simply turns a small signal, just like you heard, to a giant signal for home theater systems. And this is how we accomplish it. You can see how giant it is, but deeply inside here are the tiny components of... Oh, shoot. Now you're probably wondering, what does this have to do with Taylor series, electronics, transistors? And to be honest, a transistor can be drawn like so. Now, the way these things work is you have a base, an emitter, and a collector. And in a simple drawing, we can have a voltage applied here, let's call it V1, and a voltage here, call that V2. Now, in general, as a current is passed through voltage 1 and goes right to the emitter, oh yeah, you can see that path. Now this path we'll be calling current A. Now likewise, if we shut the emitter off and we have it just go through the collector, we can see and call this current B. Now always with a transistor of this type, current B is going to be much greater than current A. And thus we have amplified the current. Unfortunately with these, the voltage going into a transistor is not always a perfect voltage. So in this case, this is a perfect world. Now in the real world, we're going to have something that looks like this. Some really funky signal because of capacitors and real world applications of resistors that can't deliver a perfect signal. And unfortunately, the output signal is also going to replicate that, but at a much grander aspect because we're now amplifying it. So unfortunately, these minor little bumps turn into major bumps, which causes a huge problem in electronics. Now, like I said earlier, with the voltage incoming, there's not only just voltage, but there's a thing called gain, which we can represent as a G. Okay, that did not work. G, there we go. And that is going to represent our gain. Now, for the incoming voltage, the gain is almost infinitely zero. It's almost... Alright, that is our gain. Now, with a voltage as low as this, of a flat... G. Now, with a voltage as flat as this, the gain is almost zero, and that is what we want. That's a perfect world example. But, like we said earlier, we'll get these choppy little crests and peaks, which basically that gain transmits to a fluctuating gain, which in result, our output gain, which is what we hear, is going to be all the way fluctuating. It's going to be high, it's going to be low. We can't even hear it. We can't even listen to it. It's not even music at that point.
Now, amplifiers aren't just one transistor. Exactly, they are multiple. Even more, millions. They're all daisy-chained, which creates massive variables and massive fluctuation in the input. Now with that, we can take Taylor expansion of transistor governing equations. In terms of it, we can predict the gain and the non-linearity of the wave.
And that is of course what we hear, which is of course why we invent these things. It's because we want sound to sound good. Now with all the circuitry, we can use Taylor series, like I said, to predict exactly what it's going to sound like based on our circuit components and the obvious core function of the transistor.